Hello, I am Dr. Ajay Sharma, Department of Electronics and Communication Engineering, James Engineering Management Technical Campus, Greater Noida. The subject that I teach in this semester is digital communication, and the topic that I discuss in this video lecture today is autocorrelation and cross correlation, central limit theorem, and Wiener distribution. Before going into detail of autocorrelation and cross correlation, first I just give the concept of what is correlation function. Actually, a correlation function is a function that gives the statistical correlation between random variables, right? So if one consider the correlation function between random variables representing the same quantity measured at two different points, then this is referred to as autocorrelation function. On the other hand, correlation function of different random variables are sometimes called cross correlation function, right? To emphasize that different variables are being considered and because they are made up of cross correlations. So, so correlation function are a useful indicator of dependencies as a function of distance in time or space. So, just now come to autocorrelation. So autocorrelation are also known as serial correlation of a signal with a delayed copy of itself as a function of delay, right? So it is the similarity between observation as a function of time lag between them, right? So the analysis of autocorrelation is a mathematical tool for finding repeating patterns such as presence of periodic signal obscured by noise or identifying the missing fundamental frequency in a signal implied by its harmonic frequencies. So this is all about the autocorrelations, So autocorrelation are also known as serial correlation, and it is the correlation of a signal with a delayed copy of itself as a function of delay, right? So autocorrelation function, now let us consider that autocorrelation function of the stochastic process xt. Now consider a very random process xt. Xt is a random process, right? And xt is the product of two random variables xt1 and xt2. xt1 and xt2 means you have a random process xt, and look at this xt at two different time intervals t1 and t2. So this is the random process at t1 and this is the random process of t2. Random process of random variable x, the x remains the same, but we have two time intervals. So that is why we call this autocorrelation function. Same variable with same variable, we see same variable in two different times, xt1 and xt2, right? So in this way, we can write this autocorrelation xx t1 t1 comma t2 is expectation of xt1 xt2. So there are some properties of autocorrelation functions are also be noted. So autocorrelation function of a weakly stationary process xt can be expressed as rxx tau. So this is rxx tau. It's just show a autocorrelation function is the expectation xt plus tau and xt. So the same x we can see, this is the present time and this is the time after tau, So tau is a time, we shift the time t as t plus tau. So where t denotes, tau denotes a time shift, that is t is equals to t2 and tau is equals to t1 minus t2. You can say that. So there are certain properties. The number one properties, what is number one properties? If you find the autocorrelation without shifting of time, matlab there is no shift, you know, that is there is no shift, then 0 means there is no shift. Then it is the expectation of x square t, means mean square value of xt, isn't it? So if you compare, any random variable with its present form, then it is nothing but it is the expectation of mean square value, right? Second is this autocorrelation function as tau and minus tau, means if you shift the time either right hand side or left hand side of present time, then the both autocorrelations are same. If your shift is same, the amount of shift at right side and amount of shift at left side, and if you take the autocorrelation between the two, r tau and r minus tau, then both are equal, right? There is a symmetry. There is a symmetry along a present time, right? Third one is, what is this? Rx excess tau is less than equal to Rx 0, right? So whatever you calculated autocorrelation at some time shift is always less than or equal to if you have a autocorrelation at tau is equals to 0, or if you look autocorrelation without shift in the time. So this is very important, some properties of autocorrelation function, and this is the basic definition of autocorrelation that we already discussed. So look at this autocorrelation. Autocorrelation can be write as R x. R is autocorrelation x t1 dot comma t2. So autocorrelation is we have to see our random variable at two different times t1 and t2, and it is expectation of the product of xt1 into xt2, right? Now come to cross correlation. As far as cross correlation is concerned, actually in signal processing, cross correlation is a measure of similarity of two series as a function of the displacement of one relative to other. So this is also actually known as sliding dot product, right? So so a cross correlations involve two different variables, right? And in autocorrelation only one random variable involved, but in cross correlation two random variables involved. So in probability and statistics, the term cross correlation refers to the correlations between the entries of two random variable x and y, right? So two random variables involved in cross correlation. So here is the representation of cross correlation, x and y t1. So this is the expectation of xt1 into yt2. And cross correlation is measure of correlation between sample function amplitude of processes xt and yt. So we have a two separate random process xt and yt at a time instant t1 and t2 respectively. T1 is the time associated with xt and t2 is the time associated with yt. Now come to another topic, centered limit theorem. Look at the introduction of centered limit theorem. Centered limit theorem describes the relationship between the sampling distribution of sample mean and the population that the samples are taken from. come to the normal population and some important fact. If the population is normally distributed, then the sampling distribution of X is normally distributed for any sample size n. Mean if you have a population, if you have a data, right, and the data that you have is normally distributed, or we will say Gaussian distributed, right, normally distributed or Gaussian distributed, then if you take the samples, if you take some sample from that population, sample of any size n, then these samples also follow normal distribution. Get the point? Okay. I once again repeat, if the population is normally distributed, then the sampling distribution of X is normally distributed for any sample size n. I just read this paragraph in this slide and try to give some concept that involved in this central limit theorem. Suppose that a sample is obtained containing a large number of observations, right? So if you take a samples that have a large number of observations, right? Each observation being randomly generated in a way that does not depend on the value of the other observation. So if you perform number of observations and you just form a sample by having number of observation, a very large number of observation, and each observation is randomly generated, and all the generation are not depend on each other, right? And that the arithmetic average of the observed value is computed. What you have to do? You first of all, what you have to do? You take a sample by taking large number of observations, and the observation that you take does not depends on another observation. Means all the observation are totally independent. And what do you do? You take the arithmetic mean or average of that observed value, and you have to compute that value. So you have a sample having large number of observations. All observation are different, obviously, because there is some randomness involved with that. And what you have to do? You have to just take the mean value or the average of that. You have to compute it, right? Now, if this procedure is performed many times, I mean, if you do that process, for example, say at 9 a.m., right? 9 a.m. you perform certain experiment. In that experiment, you take samples. How you take samples? Take the observation of certain random variable. Note down the observation. Say if you take hundreds of observations, all observation are different because they are generated randomly. What you have to do? You just calculate the mean or expected or arithmetic average. You just note down the value. Now what you do? After certain time, say at 12 noon, what you again perform the same experiment. Again take the samples. Again take the observation to form a sample, and again you take the if this procedure is performed many times, the central limit theorem says that the computed values of the average will be distributed according to the normal distribution. Now what you have to do at 12 noon, you just repeat the same experiment that you had performed at morning 9 a.m. Again you have some large number of observation. Again you take the mean. So you collect two mean. After 2 hours, say 2 p.m., again you perform the same experiment. Take the samples that contain large number of observation. Again take the mean of that. Now you have third mean in your data. Repeat this time in whole day. For example, you perform this at say 9 p.m., right? So you have large number of data of the mean, right? And that mean comes from different. You perform the experiment that you perform after each hours or each, or you must say there is a. For example, if the time gap is 2 hours, so first mean come at 9 a.m., second mean come at 11, third mean 1, and fourth mean come to 3. So you just repeatedly do the whole day. In whole day you have a data of this mean. What central limit theorem says The central limit theorem says that all the means are normally distributed. Means if you draw the curve is a bell shaped, and you draw the curve by taking these means. So the mean is totally normally distributed or have a Gaussian distribution. This is all about central limit theorem. So if a random sample of n observation is selected from a population, then when n is sufficiently large, the sampling distribution of x will be approximately normal. The larger the sample size, the better will be the normal approximation to the sampling distribution of x. I think you all understand that central limit theorem. Central limit theorem is nothing but if you have a certain experiment, you perform experiment, and how you perform an experiment, you take the value of some random variable, and when your experiment is finished, then you take the mean of that experiment. Now you again perform the same experiment after certain time interval. Again you have follow the same procedure, and again you take the mean of the observations, and again then you attempt third time, fourth time, fifth time. So you have mean, you have a data of mean. Now the mean, when you look at the mean and when you draw this mean, the shape that you get, the distribution curve that you have is a bell shape, means it is normally distributed or a Gaussian distribution. So all the means, all the statistical average follow the normal distribution or a Gaussian distribution. As far as the Wiener process is concerned, in mathematics, the Wiener process is a real valued continuous time stochastic process named in honor of American mathematician Norbert Wiener for his investigation on the mathematical properties of the one-dimensional Brownian motion. So Brownian motion, you all know that Brownian motion, then you all read this Brownian motion in your previous classes. I think at 12th level or 10th level, this Brownian motion come in the syllabus of physics. So it is often also called Brownian motion due to its historical connection with the physical process of the same name, originally observed by Scottish botanist Robert Brown. Right. So Robert Brown is a scientist, and this Wiener, this Brownian motion comes from that name of the scientist Robert Brown. It is one of the best known stochastic process and occurs frequently in pure and applied mathematics, economics, quantitative finance, evolutionary biology, and physics. So in applied mathematics, the Wiener process is used to represent the integral of a wide Gaussian process, and so is useful as a model of noise in electronics engineering. Right. So this is just a Wiener process, just a is some theoretical type of topics. So you go through, students just go through the books and just form some make some notes on that, and memorize certain points. This is the only thing in there. No much concept involved in these type of topics, especially Wiener process or like that, right? So thank you very much.